This is Lab 4 circuits. In this lab, we'll explore the behavior of circuits with resistors and capacitors in parallel and series and use multimeters to measure the potential difference and the current. Some key concepts include Kirchhoff's current law, which states that the sum of all the currents flowing into a node equals the sum of the currents flowing out of a node. Kirchhoff's voltage law says that the sum of the voltages around a loop is zero. Ohm's law says that the current is directly proportional to the electric potential difference and inversely proportional to resistance. Equivalent resistance. When we have resistors in series, the equivalent resistance is the sum of all individual resistance. And when they're in parallel, the reciprocal of the equivalent parallel resistance is the sum of all the individual resistant reciprocals. And finally, that capacitance is equal to the charge times the voltage. So this is charge conservation and energy in series circuits. So we first predict current I1 and I2. We can use a loop rule to do this. Starting anti-clockwise, the voltage lost by the batteries is equal to the gain by the resistors. Since the resistors are in series, the currents I1 and I2 are the same, and the equivalent resistance is 147 ohms. So when we solve this out, we get 0.02 amps for the current. Our simulation matches. And we know that when the ammeter is inserted backwards, the reading does not change. When the ammeter is replaced with a voltmeter, the ammeter reads 0 volts as the circuit is open and there's no current flowing. The voltmeter reads 3 volts as this measures the potential difference across the battery. The table on the left shows the potential difference for different paths. Potential difference across a loop should sum to 0, which in this case it does. The ammeter reading does not change because the voltmeter does not cause any resistance. Voltmeters have infinite resistance, so current does not pass through them. When the ammeter is placed in parallel to the resistor, the current reads 0.06 amps instead of 0.02 amps. This is because electrons take the path of least resistance. Therefore, all the current flows through the path with no resistance, and the equivalent resistance of the circuit depends on only the 47 ohm resistor. Therefore, we get that V equals IR, the 3 volts of the battery, divided by the 47 ohms of the resistance, and we get that current is equal to 0.063 amps, which is what the ammeter measures. This slide calculates the resistance of different elements based on the previous voltage and the current. We can see that the resistance for each of the resistors is close to theoretical values, and the wire and batteries have no voltage and therefore will have no resistance. Next, we are going to look at RC circuits. We're going to simulate an RC circuit with a 10 ohm bulb, a 20 ohm bulb, one 9-volt battery, and a 200 microfarad capacitor. First, I connected the batteries to the 10 ohm bulb and the capacitor in series. First, the light bulb will start off bright, and it immediately dims as the current decreases due to the charge buildup on the capacitor. The light bulb goes out when T is much greater than 0, as no current flows through the circuit, as there is buildup on the capacitor. When disconnecting the battery, and connecting the capacitor directly to the 10 ohm bulb. Again, the light bulb starts off bright with the current in the opposite direction. It immediately dims as the current decreases due to the charge on the capacitor. And finally, the light bulb goes out when T is much greater than 0 as no current flows through the circuit. For the 10 ohm resistor, the charging time was 7.4 seconds and the discharging time was 13.4 seconds. For the 20 ohm, the charging time was 12 seconds and the discharging time was 30 seconds. This makes sense as approximately doubling the resistance doubles the discharge and charging time. So here we have a plot of voltage and ln V over V naught. As the charge on the capacitor decreases, the voltage across the capacitor decreases and the current through the bulb decreases. Therefore, a plot of ln V over V naught versus T should yield a straight line with the slope of 1 divided by RC. RC is called the time constant of the circuit, and this is the time at which the voltage difference had dropped to 1 over E of its original value. So from the experimental value, we know that this is going to equal 0.2 times 3, which is 6 ohms, and our theoretical value is -1 over the slope, which is -0.114, which is 6.58 ohms. So what if we were doing this lab in real life and used an actual ammeter instead of a simulated ammeter? A real ammeter would not have 0 ohms of resistance. The current reading would be lower since the current is inversely proportional to the resistance. An increase in the resistance will decrease the current. What if we were doing this lab in real life and used a real battery to charge with no resistor? The capacitor would immediately be charged since there's no resistance, and the voltage drops due to the light bulb. All components have resistance, however, so the time would still be required to charge the capacitor.